So, you have one single, monumental physics problem. But what's really amazing is that to solve it, engineers came up with two completely different answers. Two bombs with two totally unique designs. This is the story of how they actually worked.
Okay, so here they are, Little Boy and Fat Man. One was a pretty straightforward gun-type weapon that used uranium. The other? A way more complex implosion device built for a different element, plutonium. You can see they look different, and that's because they were fundamentally different, each designed to solve the same problem in almost opposite ways.
So, the big question is, how? How did these two completely different machines get to the exact same world-altering result? The answer is just a masterclass in physics and engineering. So, let's dive into the mechanics. You know, it all starts with the fuel. The project needed uranium. But here's the catch. Not all uranium atoms are the same. See, most of the uranium you dig out of the ground is an isotope called uranium-238. It's not fissile, which is a fancy way of saying it can't create that runaway nuclear chain reaction you need. The real prize, the secret sauce, is a much rarer isotope, uranium-235. So to get enough of that precious U-235, you have to painstakingly separate it from all the U-238. This whole process is called enrichment, and the goal is to massively boost the concentration of the fissile U-235. This was an industrial challenge on a scale that's, well, just staggering.
So how on earth did they solve this separation problem? It's pretty clever, actually. They turned the uranium into a gas, and then they spun it at absolutely incredible speeds inside a machine called a centrifuge. Just think of it like a really fast merry-go-round. The slightly heavier U-238 atoms get thrown to the outside wall, while the lighter and much more valuable U-235 atoms kind of cluster near the center, where they can be siphoned off.
And this chart really just spells out why that whole process is so critical. The uranium you find in nature, it's less than 1% U-235. For a nuclear power plant, you need to enrich it to about 5%. But for a weapon, you've got to get it all the way to 90%. You literally have to remove almost all of the U-238 to get a material that will actually explode.
Okay, so you've got your highly enriched fuel. Now, how do you actually trigger the reaction? This is where the two designs really split off into completely different paths. One is basically a brute force method, the other is a work of incredible delicate precision. First up, we've got Little Boy. This one used what's known as the gun method. And honestly, it's exactly what it sounds like. It's basically a massive cannon, designed to fire one piece of uranium directly into another. So here's the play-by-play. Conventional explosives go off and boom, they fire a uranium bullet down a gun barrel at over 600 miles per hour. Waiting at the other end is a uranium target. The bullet slams into the target, the two pieces merge, and suddenly you have what's called a supercritical mass, a density so great that a chain reaction is basically guaranteed. To give it a little nudge, tiny initiators shoot out a burst of neutrons, and that runaway reaction begins. Simple, really, but brutally effective. Fat Man was a whole different animal. It relied on a far more elegant and, well, much more complex idea: implosion. So instead of slamming two pieces together, this design squeezes a single piece of plutonium from all sides at once with just unimaginable force. Now, the core idea here was a total stroke of genius from a physicist named James Tuck. He pictured using explosives that were shaped in a very specific way, so they would act like lenses, focusing all that explosive power inward instead of outward. But the math to make that actually work? Just incredibly complex. It took a mathematician named John von Neumann to perfect it. This design was absolutely necessary for plutonium, which is way more unstable than uranium. A slower method, like the gun design, would have just fizzled out. So as you can see here, a whole bunch of explosives detonate in this incredibly precise sequence, creating a perfectly symmetrical, spherical shockwave. It's kind of like squeezing a tennis ball from every single side at the exact same instant. This shockwave hits the plutonium core, compressing it to supercritical density almost instantaneously, and that triggers the chain reaction before the bomb has a chance to tear itself apart. Now, having a working trigger is one thing, but making sure it goes off at the precise, perfect moment, that's a whole other challenge. To get the maximum destructive effect, both bombs were designed to detonate high up in the air, not when they hit the ground, and that required a really sophisticated sequence of timers and sensors. Let's just walk through those final seconds, shall we? So after the bomb is dropped, a timer kicks on the internal battery. Then at about 1,900 feet, barometric sensors, which basically measure air pressure to figure out the altitude, they close a circuit. This was a critical failsafe, right?
It was there to prevent any stray radio signals from setting the bomb off too early. This then arms the final trigger, a set of radar altimeters that bounce radio waves off the ground to sense the exact height, and then fire the weapon.
And what happens in that tiny fraction of a second? Well, it's all about nuclear fission. To put it simply, a little neutron hits a big, heavy nucleus like U-235. The nucleus absorbs it, gets really unstable, and splits apart. This releases a tremendous amount of energy, and 2 or 3 more neutrons. And guess what? Those neutrons then fly off and hit other nuclei, creating a cascade, a self-sustaining chain reaction that just unfolds in a flash.
The result of that uncontrolled chain reaction is an explosion on a scale that's almost impossible to imagine. Both the gun method and the implosion method were really just different keys designed to unlock the exact same devastating force. To put that force into some perspective, just look at these zones of destruction. The central fireball instantly vaporizes everything in about 1/3 of a square kilometer. Just gone. The blast wave then causes severe damage, total destruction, out to 4.5 square kilometers. And moderate damage, which is still incredibly destructive, extends out to nearly 9 square kilometers.
So, we've seen the two ingenious yet terrifying solutions to the problem of nuclear fission: the gun and the implosion. 2 different roads to the same destination. But the final question isn't really about engineering. I mean, these designs solved a physics problem for sure, but what new problems did they end up creating for all of humanity? Now that's something to think about.